Hey guys, welcome to this talk. So today we're going to talk about understanding random numbers in computing. Thanks for joining me. My name is Benjamin Williams. I'm a PhD student here in the School of Computer Science, University of Lincoln. I'm also a research assistant, and I use random numbers quite a lot in the work I do. So, if you've done any kind of computer science, you probably know that random numbers comes up quite a lot, especially in things like games development, which is my particular area of expertise. Random numbers comes up quite a lot, and that's what we're going to talk about today. We're going to kind of talk about how we can generate random numbers, not just how to use random numbers, but actually understanding how that generation process takes place. So thanks for joining me. I do appreciate it. It's quite early in the morning. But if you have any questions throughout this, I do have my comments thing on the other screen. So just feel free to ask me any questions, and I'll be more than happy to answer them. I quite like this kind of back and forth where you guys ask questions and I can kind of answer them. Equally, if there's something I need to repeat or I'm going over it a bit too fast or a bit too slow, just let me know in the comments. I'll be more than happy to oblige to your requests. But yeah, that's what we're going to talk about today: understanding random numbers in computing. So it's exactly as the title kind of gives away, I guess. And this is one of my favorite things to talk about, actually. I think understanding random numbers is sounds on the face of it sounds quite boring, I guess. It's really exciting topic. I love talking about this, and I usually talk about this every year to the games computing students. Usually in the context of PCG, so how you can use random numbers in procedural content generation, and we'll kind of touch on that today. But to give you an idea of where we're going, so there's two things I want to talk about in this. The first thing is randomness and PRNG. So the main bulk of this talk is going to be about this topic. So randomness, what randomness is, what pseudo-randomness is, and PRNG. So PRNG stands for Pseudo Random Number Generation. If that's a bit complicated or whatever, don't worry, we're going to talk about what that means and stuff like that. So that's in the first half, we're going to talk about randomness and PRNG. And like I said, this is going to be the bulk of the talk, right? It's going to be mostly focused around these two things. At the end, however, we are going to talk about coherent noise functions. And I'm not going to go into much detail here because it's, well, firstly, it's a fairly, it's not a full 60-minute talk, but also coherent noise functions is usually used for, games development. And also, I'd just like to kind of signpost you in the direction of coherent noise functions. But they're equally a really interesting category of random numbers. Really interesting. I definitely recommend you check them out, but we'll talk about them and what they are at the end. But we're not going to go into, mad detail about coherent noise functions. The main part of this talk is randomness and PRNG. So just to kind of, show you, we're going to talk about that stuff at the end very briefly. So it's mostly all of this today. We're going to talk about randomness and PRNG. And just to kind of break that down even further, we've got three objectives here, really. So at the end of this, hopefully you should be able to understand what randomness is and why computers find it hard to generate. As humans, we have this kind of natural way of generating random numbers, and understanding pseudo random number generators, so PRNGs, how to use seeds and use those seeds for number sequences, and understanding coherent noise as well. So at the end, hopefully, we will talk about coherent noise. Now, I've just had a question from Primex Andy, which is an interesting thing. Are you able to link PRNG to regression models and repeatable results? So if I understand the question correctly, I think you can. I'm not too familiar with regression models themselves, but you can definitely use PRNG for repeatable results, partly due to this state determinism property of PRNGs, which we're going to cover in this. PRNG is a really interesting kind of topic, especially when we talk about things like how we can fool statistical tests using PRNG. So yeah, hopefully we're going to talk about PRNG and how we can use that to get repeatable results. In fact, the property state determinism of PRNG algorithms, it is really interesting because you can use that for so many different things. And I'm not too sure if I've answered that question correctly, but hopefully that gives you some insight to that. So I just want to start on this question, and it is, what is randomness? Because I got asked this, I can't remember, I think it was 2-3 years ago, while I was giving this talk, because I was talking about randomness, and somebody asked, well, what is randomness? And it's a good question. Randomness by its nature is quite hard to define anyway. Inherently, randomness is quite hard to define. So we've got to think about what actually is randomness, because there's few schools of thought regarding this. And I just got a comment from Primex Andy. That's brilliant. I'm glad it answered. glad it answered your question. So to talk about what randomness is, I want to go back to one of the most ubiquitous examples of randomness, and probably the most popular one you can probably think of, is coin flipping. And we consider coin flipping generally as a random process. I suppose there have been papers out there that show that actually humans flip coins very predictably. And we can kind of get how we can predict the result of a coin toss based on the angle and the distance and so forth. But generally, we flip coins, the heads or tails thing, to decide two outcomes, right? So we have heads, you do something, tails, you do something else. You can kind of think of this as like a two-sided dice. But the point is that this coin flipping process, we generally consider this as a random process, right? So if you don't know what to do and you've got two choices, you flip a coin for it. And I do this sometimes. If you have two choices of what to eat, you can flip a coin. Heads is something, tails is something else. But yeah, we generally consider this process to be random. But the question is, why do we consider coin flipping to be random? And if we can explain why coin flipping is considered random, maybe we can get at the root of what we asked in the previous slide. What is randomness? So the reason we consider that to be random is because there's a hell of a lot of variables involved in a coin flip. I know coin flipping is literally you flick it with your finger, and it seems like quite a simple process, but there's so much variables going on with that process that it's really hard to predict the state of the coin at any one point. So it's really hard to predict whether the outcome will be heads or whether it will be tails. So, for example, in a coin flip, predicting the exact path of a coin and the outcome, as a result of a coin toss, is very hard because there's so many human elements. There's things like the amount of power you put into the flick. There's the angle that you flick it at, the distance, the distance from your hand to the floor, and also things like the catch method. How do you catch it? Do you catch it and then put it on your hand, and do you catch it mid-air and so forth? So there's so many different elements there about how to flip a coin. I mean, these are just a few of them. There's so many different elements. I mean, there's physical elements as well. So things like wind, wind might have some bearing on whether or not this coin flips from heads to tails. Things like the coefficient of restitution. So if it hits a hard surface, does it bounce back, and this kind of stuff? There's so many elements in just a single coin flip. The human kind of element of it makes it quite a random process, and it's very hard to determine whether or not it'll be heads or tails, which makes it a great process for generating random numbers, right? But this is why we consider it random, is because predicting the exact path and the outcome of a coin toss is really hard because of all the variables involved in that process. In order to predict a coin toss accurately, you'd have to take all these variables into account, and from that, put it into some kind of model, and that model would predict whether or not the coin is going to land head side up or tail side up. So it's a really interesting question, and even things like tossing a coin, if you stop and think about how many variables is involved in that process, it's such a it's quite interesting. So predicting all of these elements together to make up the state of that coin toss is quite a difficult thing, very difficult. So in this sense, you can kind of think of randomness as unpredictability, right? if something is very unpredictable, and if determining the state of something at a given point is very hard, it's very unpredictable, then we can kind of think of this as randomness. And I have put a note down here. That's one school of thought. This is the way I like to think of randomness. Is it's essentially just unpredictable. So you can kind of interchange these terms, randomness and unpredictability. Another school of thought is regarding statistical tests. So you can have a very clear-cut definition and say that randomness is something that beats the statistical test. So if it can fool a statistical test, then it's random. And actually, that's how we test PRNGs. I'll get on to PRNGs, but algorithms for generating random numbers. This is how we can test if they're actually good at their job, is using statistical tests. But yeah, just this is how I like to think of randomness, unpredictability. Now, computers and randomness is an interesting topic. So far we've just talked about coin flipping, but that's got nothing to do with computers. And this talks about computers. So it turns out that generating random numbers with a computer is actually quite a hard problem. And the reason is that the problem ultimately lies with determinism. Computers are really good deterministic machines, and the name there, machine, kind of gives it away. Computers are very good at repeatable results. So if you put in a certain input, you will always get out a certain output. But with randomness, we're kind of asking for something that isn't deterministic. It's undeterministic. So how do we get these deterministic machines, things like computers, to generate undeterministic things for us? It's quite a hard problem. I remember considering this process before I learned about randomness, and I thought that's nearly impossible. How do you do that kind of stuff? And there's a couple of solutions, and we'll get onto it. But yeah, generating random numbers with a computer is quite hard. It's quite a hard task because computers are by their nature, deterministic machines. How would you get something that's deterministic to generate something that's undeterministic? That's a really hard process. So as an example, to highlight this, consider how we might generate random numbers. So if I asked you, give me a random number between 1 and 10, your brain's going to interpret, that kind of command, and you're going to come up with maybe the answer 6 here through free will. So I say, give me a random number between 1 and 10. You think about it and you go, oh, right, 6. But you've arrived at that process. You've arrived at that result, 6, through free will, right? Now, the issue here is computers don't have free will. And if they did, I always say this, but if computers had free will, we'd have a hell of a lot more problems on our hands than generating random numbers. Because essentially you'd have a computer that would just do whatever it likes. And computers don't have this because they're deterministic machines. So how do they actually do that? How do computers generate random numbers without free will? Well, there's two main methods, and we're going to talk about each of these individually. The first is sampling, right? So essentially, you sample with some kind of sensor or some kind of process a truly random source, and you use that. And this is sometimes called HRNG, hardware random number generation, because you usually have some kind of hardware like a sensor that will sample the outside world and give you some kind of random numbers based on that. So that's one way, is you don't go through an algorithm. You just say, hey, just sample something that is random in the world. Whether that's coin tosses. Obviously, you can't have a computer that samples coin tosses, but you could think of coin tosses as, if it lands as heads, it's 1, and if it lands as tails, it's 0. And if that's the case, you could build a number quite easily out of coin tosses. So you could think of that as a random source as well, but obviously it's impractical. And we'll get on to what we can sample. The other way is mimicry, right? So we can approximate randomness via some algorithms, and this is where we get into pseudo random number generation. So yeah, there's two ways to this. We either sample something, or the other way, we just approximate randomness through some kind of algorithm. So the first way, sampling, is probably the easiest to understand. So you have something like this on the left, which is just a card that samples something which is random, and it generates random through some kind of physical process. any physical process. In theory, you could do coin tosses because that's a physical process, but obviously there's no way of putting that on a circuit board or anything. So most of the time we use hardware number generation for things like cryptography, where the randomness of something is really important. So when we need kind of beefier random numbers, we can use hardware generation of random numbers for this particular task. And usually this samples some kind of low-level noise source, so something that is very unpredictable, something we could look at and not understand the exact state of that thing at any one time. So things like thermal radiation, nuclear decay. So looking at I don't exactly understand it myself because I'm not a physicist, but as far as I'm aware, you can look at a radioactive element, and then based on the nuclear decay of that, you can get some random numbers out of that. And things like atmospheric noise, so electronic noise, that kind of stuff, the static you see on a TV, you can sample that kind of stuff and use it for random number generation. And there are esoteric kind of generators out there. So Cloudflare, if you've heard of them, they use a wall of lava lamps because they use a wall of lava lamps, and predicting the state of those lava lamps at any one point is really hard because lava lamps are quite unpredictable, and they use this to generate random numbers. So there are a couple of esoteric ways of generating random numbers through sampling as well. But yeah, usually this is how we do it, is sampling. We just have some kind of circuit board like here on the left, and that just using some sensor just samples something that's random. But it's also worth mentioning there's other random sources. So things like if you're running on Linux, there are ways of generating random numbers by looking at junk data that's pushed to a particular place. So here's some other familiar random sources. So rolling dice, that's a good way of generating random numbers. Shuffling a deck of cards in itself is quite a random process. Determining the exact state of the cards at any one point is really hard. And things like TV, white noise or static is atmospheric or electronic noise. So that stuff, here's a couple of random sources that you might be familiar with. But you could essentially, you could use these as a way of generating random numbers. So I've just got a question from Primex Andy here again. So it asks, is noise from diodes still used in hardware and RNG? It was used in ERNIE with premium bonds. It seemed so simple. Just wondering why it might not be used anymore. So unfortunately, I'm not too sure myself. It's an interesting question. I'm not exactly sure. I'm not sure what ERNIE is. But as far as I'm aware, most hardware RNG, so that there are a couple of ways of doing it. There are, and I'm not sure if this helps, but there are ways of sampling something that's random, like electronic noise. The other way to do it is to actually use a circuit itself on the on a chip or something like that to generate some kind of random process, random numbers through some kind of circuit. So essentially using something like a pseudo random process, but actually baking it onto the board itself. So some Intel chips, I think, and some AMD chips as well, have an instruction set for generating random numbers themselves. So unfortunately, I'm not too sure of the question, but hopefully that it gives you some answer, I guess. So yeah. Anyway, to continue on. So the other way we've talked about sampling. The other way to do it is through mimicry. So usually we do this through a PRNG. So we use some kind of algorithm to produce numbers which appear random, right? So instead of sampling this kind of stuff, we use some kind of algorithm to generate numbers that look random. Okay. Now, in most cases, in some cases, this can be faster than HRNG, depending on the actual generator itself. So very simple PRNGs like linear congruential generators are a lot faster than things where we have to actually sample a source and then pipe it through the bus and this kind of stuff. But other algorithms like the Emerson Twister actually take quite a lot of time to generate random numbers. So in theory, PRNG, depending on how random you want your results to be, can be a lot quicker. And essentially, this is a deterministic process to generate undeterministic results. That's essentially what it is, right? I've just got another question here, again, by Primex Andy. So just wondering why static noise from TV would be considered easier than a diode. So it's a good question. I think really it depends on how random you want your numbers to be. Things like cryptography rely quite a lot on numbers being very random, very unpredictable. So we use something like sampling from white noise from a TV or something to infer some kind of random numbers from that. Sometimes, so most of the time when you use something like a hardware generator card rather than it being built onto the chip, you're looking at cross-platform results. So if you're writing cross-platform software that relies on a particular instruction set on a particular chip, going down the route of circuitry and stuff sometimes isn't the best idea, because some chips support random number generation, some don't. Whereas using something like a static noise from a TV, I mean, you could have a hardware card or something, but then again, you're tying it to the hardware. The other thing about using something like TV noise is that you could have this streamed from some kind of source on the internet, or I don't know. But usually, yeah, you use outside sources like white noise for when you want really beefy kind of random numbers, I guess. So hopefully that helps answer that. But yeah, that's the gist of it, I think. But anyway, we'll continue on. So we're talking about mimicry here. So yeah, usually we do this through PRNG, pseudo random number generation. That's what it stands for. So let's talk about PRNG. This is the kind of part of the talk where we're literally just going to talk about PRNG now. And it got confirmation from Andy. That was a good answer. Brilliant. Thank you. So yeah, the first thing I want to ask is, we've talked about what randomness is, right? So we've talked about randomness, and one idea we can have is randomness as unpredictability. So when I talk about pseudo random number generation, what the hell is pseudo randomness, right? And all pseudo randomness is really it's an approximation of true randomness, and I've kind of touched on this earlier, where we talked about we're mimicking true randomness, right? We're approximating something that is truly random using usually some kind of algorithm. So just as if this thing on the left, this quite poor drawing of a dice, approximates the real thing on the right, you can kind of think of pseudo randomness as the thing on the left and true randomness on the right, which kind of approximating that process. So here's a good definition of what pseudo randomness is. I can't remember exactly where I got this from, but it says a pseudo-random process is a process that appears to be random but is not. Pseudo-random sequences typically exhibit statistical randomness while being generated by an entirely deterministic causal process. So just to break this down, it says here that appears to be random but is not. So something that mimics randomness. That's all this means. So we're just mimicking true randomness. When we talk about exhibiting statistical randomness, we usually mean that it can fool statistical tests. And here it says, while being generated by an entirely deterministic causal process. I've talked a lot about this, PRNG, and I've said, oh, they're just algorithms for generating things that look random. But how do we actually do this? How do we generate stuff? Well, this is what PRNGs are. they're just ways of doing this. And we're going to talk about how PRNGs work. So PRNGs are just algorithms for generating pseudo-random values. Usually, now I say usually because some PRNGs, like linear shift feedback registers and stuff like that, work a bit differently. But most PRNGs have this kind of internal state that we set using some kind of seed, right? And this state ultimately affects the random output. And every generation of that, every time we ask for a new random number, that state changes. And if this is confusing, I've got like a bit of a diagram on the next few slides. And usually if you don't provide a particular seed to set the state with, we just use the time by default, because time is always counting up and it's always going to be a fairly unique number, right? So that's what PRNGs are. We can generate random numbers using these PRNGs. So PRNGs are just algorithms for generating pseudo random numbers. So numbers that approximate true randomness. So here's my kind of diagram of PRNG. So here in the middle, we've got a PRNG, a pseudo random number generator, and as it says in the top right, PRNGs take some kind of input number and just transform it to some kind of a random output. And I have to preface this by saying that this is most PRNGs. That there are some PRNG processes out there like canonical random number generators, or like I said, LSFRs or twisted LSFRs that go about it a bit differently. But most PRNGs, things like linear congruential generators, twisting algorithms and this kind of stuff, they use this kind of process where we take an input state and we transform it to some kind of random output. So yeah, this thing in the middle, just think of this is the PRNG. So the thing on the left here, we call the state. Now if we're setting this manually, if we're saying that this state is a particular number, and state doesn't just have to be a number either. It could be, I don't know, an image, right? It could be a whole array of different values. But for the sake of simplicity, we're going to think of this as just a number, right? Just an integer. So the state, if we set this initially, it's seeded with it. It's called seeding the state. We're setting that state manually. So let's seed this PRNG with for example 15. So if we seed it with 15, we just get 15 here. Now if it depends on what kind of programming language you're in. In C++, for example, there's this I can't exactly remember the thing off the top of my head. I think it's seedmt maybe, for seeding random number generators. In C#, it's quite easy. You can use system.random. This particular one, random.init state, belongs to the Unity game engine. But yeah, essentially all we're doing is we're setting that state initially to 15. We're initializing this PRNG. We're seeding the PRNG with the value 15. And that's all it's doing. Is this thing on the left is the state, and we're just setting the state to 15. On the right here, this is the output from the PRNG. So after the algorithm has ran, it sets this output to some value, right? So what's going to happen is it's going to take that state, do something with it, and it's going to set the output to that result, basically. So on the left we have the state, and on the right we have the output. So if we call something like this, where we say, hey, random.range 0 10,000, we're asking for a random number between 0 and 10,000. And again, there's a bunch of different ways of doing this. If you're using C#, it's random.next. If it's C++, it's rand. Python has, I think, random.randrange. There's a whole bunch of different ways of doing this. This particular one, random.range, again, is the Unity game engine. So all this is doing is it's just asking for some kind of random number between 0 and 10,000. So what happens when we call this? What actually happens in the PRNG itself? So we take the state, 15 in this case, and we pass it into the PRNG, right? So it essentially, I've got this diagram here of a PRNG kind of being like a circuit. You can imagine it kind of being piped along a bus to the PRNG itself. And the PRNG receives the input, and PRNG doesn't really say 15 here like it's received it, but this is how I like to think about it, is the PRNG receives that input, receives the state, and it says, yeah, cool, I've got the state, that's brilliant. And then something happens here where we take that state, 15, and we just use some kind of algorithm to convert that input to some kind of random number. And this is where the meat of the PRNG comes in, I guess. And there's a bunch of different ways of doing this. I'm not going to get into all the ways of doing it, but here's one particular type of random number generator. Now this is I think this takes the form of a linear congruential generator, an LCG, or maybe in some cases this might be a canonical one. But essentially what we do is we take the state, so in this case it's 15, and we have this kind of formula here where we take S, right, and we just shove in 15 where S is. We times it by 48271. That's just an example of a very big prime number. And then we modulo it by this massive number massive number on the right, 2147483647, which if that's confusing you why that's there, that number on the right is actually the maximum signed integer value for a signed integer. So all we're doing is we're timesing state by some giant prime number, and then we just modulo it by a this particular value on the right. But this is just one form. I've got to stress this is a very basic PRNG. The more complicated examples use a hell of different processes for actually generating these random numbers. But the point I'm trying to get at here is that there's an input state. It gets passed into the PRNG. The PRNG does something with that. In this case, it does this formula, and then it transforms it to some output number. So in this case, if we put in 15 and we run it through that formula, we get out 6198, right? And then this is probably one of the most crucial steps of the PRNG, is we take that output and we set it to the input, right? And then essentially when you ask for a random number next time, it's using the state. It's using that that output as the input, right? So if we generated this again, we might get 81, for example. And if we did this even more, 81 would be set to the state, and then we'd use it again. And this is how we can generate random numbers. And this is one particular way of doing it, but this is the kind of architecture of most PRNGs. Is we use this kind of process of we have a state, we do something with the state. In this case, we did some multiplication and some modulo, and then we set that output state to something, and then the output state gets set back to the state, basically. So that was a very basic example. That was a form of linear congruential generator, but hopefully that all made sense. Hopefully, you kind of get that there's this state, and all the most PRNGs do is they take that input state, they do something with that input state, they transform it using some maths or some bit shifting, some mad stuff, and then they set, they give an output value using that transformation, and then that output value gets set back to the state. And then when they call it next time, we have this process of taking the output, putting it to the state, using the state, transforming it, and going round and round. Here's a more modern example. So one of the most popular ways of generating random numbers, and in fact, if you've generated random numbers in things like C++ or C#, this is the default way of generating random numbers. So the one I introduced before, introduced before was a linear congruential generator. So linear congruential generators, for a while, they were the most popular way of generating random numbers, and they are a decent way of generating random numbers. But this was years ago, and people started to realize that like an LCG repeats itself quite a lot, and it's not really good for what we want. We need a general purpose algorithm that will give you pretty beefy answers, pretty beefy random numbers, but also runs quite fast. And this is where we get into the Emerson Twister. I just had a comment from Subpanda 101. Emerson Twister is quite interesting. I've had to look into it and get some. Yeah, so that's a good point, actually. I mean, I know it's not a question itself, but the Emerson Twister is quite interesting. I came across the Emerson Twister when I was writing C++, and I thought, the talks of random numbers and stuff, and we use random numbers quite a lot. I was always wondering what this weird algorithm was called MT19937. And yeah, we use things like the Emerson Twister in things like networking. It can be used in things like cryptography, although usually we have some fairly more beefier random numbers, so actual sampling of random sources and this kind of stuff. But it's interesting, yeah. Networking is a good example of where we might use this. But yeah, to carry on, so a more modern example is the Emerson Twister. This is the kind of de facto standard of random number generation now. Usually, if you generate a random number in some programming language, it's using this Emerson Twister. And the name is probably quite confusing. So it's called the Emerson Twister. I'm not sure if you guys know, but it's named after the. We just got a comment from Chris. Honestly, it sounds like a dance tune from the 1950s. That's a good point. Actually, I've never thought about that. It does sound like a 50s dance move. I've never heard anyone come up with that comment, but that's a really good point. But yeah, the Emerson Twister. It's called the Emerson Twister for two reasons. The Mersenne part is named after a French mathematician who most famously came up with the Mersenne primes, and Mersenne primes are really good for things like cryptography, and they're a form of prime. So we essentially do 2 to the n-1, and that gives us a Mersenne prime. Twister comes from the particular type. I know it does sound like a dance move, but it does. It comes from the way the random numbers are generated. So it uses something called a twisted linear shift feedback register. So using that kind of approach, we come up with the name Mersenne Twister because it's based on the Mersenne primes. And in particular, you might hear it being called the MT19937, which is quite a catchy name for an algorithm. The MT obviously stands for Mersenne Twister. 19937 is the 19,937th Mersenne prime, and we use this in our generation. So a Mersenne Twister looks very similar to what we looked at before. Before we had this process of taking the input, transforming it, and setting the output state to it, and then setting the input state based on the output. So we're going from state 1 to state 2, state 3, and so forth. The Mersenne Twister is very similar, right? And this is a very basic abstraction of what the Mersenne Twister does. But there's essentially, instead of one transformation, we have two here. So we have essentially one process which twists the state, so it transforms state 1 to state 2 and state 2 to state 3. And we also have this secondary process where we temper the results. So if we want a random output, then we use another function to temper that result, so modify the state into a random number. So it's very similar to what we looked at. It's a slightly different, but the biggest difference here is we have two processes. So instead of just setting the input state based on the output, we're doing a separate process where we kind of split off and say, here's a random output, and then we use a separate function for twisting that state. The biggest difference here, however, is the actual state. So the state isn't just one number. It can be up to a 624 dimensional vector. And if vector is quite confusing, you just think of this as an array of numbers. So states can be 624 dimensional, and outputs can also be 624 dimensional. So we're not just talking about one number here, we're actually talking about arrays of numbers. But yeah, that's the two main differences, is that we have two functions instead of one. So we have f, which is twisting the state from one to another, and we have g, which is kind of taking the state and tempering this to give us a random output. And I'm not going into much detail of how the algorithm is, mainly because to understand details and stuff, we have to talk about bit shifting. I'll be here all day really talking about the Mersenne Twister. But using this, you could probably go off and understand the Mersenne Twister in some detail. Got an example from Chris. Can you reverse the algorithm, essentially untwisting it? So that's a really good question, actually, because it gets into the nature of twisted LSFRs. As far as I'm aware, no, you can't, because essentially to go from state 2 to state 1 using this twisting process, the previous values in the shift register is quite understanding how to go from state 1 to state 2. One way is quite easy, you bit shift, but determining state 1 from state 2 is really hard, and you can kind of think of it as a hash function almost, and this is kind of why we have two functions. We're taking one state, transforming it to the next. But yeah, it's a good question, actually. It's something I was hopefully going to point out, is that going from state 1 to state 2, and essentially, in all these random number generators, not just this one, going from state 1 to state 2 is quite easy. Going forward a state really easy because we know how to do that. You can just say, okay, cool, take the input state, do some stuff with it, set it to the output state. But going backwards, that's a lot harder. Taking an output and understanding how we went back from that can be quite hard. In the more simple ones like canonical random number generators, quite easy. It's essentially just reversing the process. But here, the function that takes state 1, state 2 is actually quite complex. We essentially take an array, a giant 624 dimensional array. We do some kind of bit shifting and we shift values in the register, and then based on those values, we use some kind of algorithm to twist the state from 1 to 2 and so forth. But yeah, going back is very hard. Going forward, really easy. And I suppose that's the goal of random number generating, is that it's really easy to arrive at an output quite easy. You can use some kind of deterministic process to do that, but by their nature, random number generators have to be quite hard to go back the other way. Otherwise, I could take some random number that you give me, like, oh, you've generated 50, right? And I could go, cool, right? I could go back from that and I could understand what the initial state of that random number generator is. And based on that, I could just generate, I would know exactly where you are in that cycle of numbers, and I could just generate whatever random numbers I want, and I'd know exactly what your state is. So yeah, it's a really good question. But hopefully that answers it. But yeah, let's carry on. And like I talked about, it's not just one number here. You can think of this essentially as state 1 actually contains many numbers. In this case, it's got, what's that, up to 16 numbers, right? Or, oh, sorry, not 60, I'm reading that wrong. Up to 6 numbers, right? And, we've talked about PRNGs quite a bit. We've talked in detail of how they work. I just want to discuss the properties of PRNGs because these are quite interesting. So the first is one I mentioned at the start. We got a question kind of involving this state determinism rule. So most PRNGs have this property of state determinism, which I always think is a bit weird for PRNGs, because PRNGs are undeterministic. So why are they deterministic in some sense? So state determinism just says that a PRNG will always output the value y for the state x. So if we have, here on the left, x is 5, we'll always get out, say, 7. And if we run this over and over again, we will always get 7 out. And that kind of defeats the purpose of a random number generator, I guess. But the point is that for a given state, we will always get a certain output. The random numbers we generate is actually based on the kind of, we have a state on the left, and it will always give us an output on the right. But in a cycle of numbers, this actually it gives us quite good output. But yeah, this is what state determinism is that on the left we have some number like 5. If we have the state 5, we will always have the output on the right that is the same. And yeah, we've got a comment just saying from Subpanda 101. I guess that would be similar to Minecraft seeds. Yes, entirely. You can kind of think of this as seeds, right? I talked about seeds and how we can set a seed and based on that get a certain cycle of values, like a certain sequence of values. You can think of it like this, yeah. So we have a seed x on the right. We will always get a y, and if we abstract that a bit, you can kind of think of it as x being the seed for the map on Minecraft and y being the map. For a seed, we'll always have a particular output. So this is what this rule is state determinism. The next is the avalanche effect. You might have heard of this in cryptography, but small changes in x massively affects the output y. So here on the right, I've got an example of this. If we go from 5 to 6 to 7 and 8 and 9, this is going up by 1. But based on that state determinism rule, you can see that the 5 gets mapped to 15, 6 gets mapped to 7. You can see that it takes something on the left and changes it to something on the right, which looks completely different. And we can think of this as the avalanche effect. This is what kind of makes it random. And the third property is probably the most easiest to understand. It's just normalization. So PRNGs can be normalized. Usually, we take PRNGs. You have some kind of upper bound of like what range of numbers it will generate, you can divide by that number, and we can normalize those values. So we can get a value between 0 and 1. And this is really useful for us because we can take that random number, which is just a float, like 0.5, or here on left, we've got 0.532, for example. If we times that by some value like 100, we will get values between 0 and 100. So we can actually, by having it normalized, we can use that normalized value to expand our range of random numbers to whatever we like. And this is usually a property that comes with PRNGs. So yeah, that's 3. State determinism. If we have a state X, it will always give us a state Y. State X, it will always give us a value Y. Avalanche effects, so small changes in X will massively change outputs in Y, which is kind of the opposite, I guess. And then finally, normalization. The next thing to talk about is random number sequences, and I'll quickly go through this because I realize we're getting close to the time, but that's okay. So yeah, for a given seed 15, for example, if we call random, like rand to generate a random number, we might get the answer 5 out. And if we call random again, we might get 85 out. So it's funny, actually, we got that comment from Subpanda about seeds, how we can take something like a seed 15 and generate an entire map from that seed. And this is the power of random number generators, and using that state determinism where we can generate entire number sequences from one particular number. So seed 15, for example, will generate a number sequence beginning with 15, 5, 85 because of that state determinism rule, right? I've just got a comment from Primex Andy, which is a good comment, actually. I think I am seeing why you wouldn't use a random hardware generator, because you can't repeat them. It's the seed that allows you to repeat the random number sequence. Yes, that's a really good point, actually, and it's something I wasn't going to bring up, and it's really good you pointed this out. Is that, yeah, sometimes we want to use PRNGs because of these properties, where we're using state determinism. So, for example, here, because we go for a given state X, we always get a Y. We can generate huge number sequences based on one seed, and that's really powerful for a bunch of different things, particularly in procedural content generation in video games. We can do a whole bunch of different stuff. But yeah, that's a good point. Sometimes you actually want to use that state determinism thing. You don't just want a completely random source all the time. You actually want something that will give you a has this kind of predictable kind of thing to it. So yeah, that's a really good point. Yeah, so to get back to number sequences, so hopefully this makes sense. And from this, you can build very complex sequences. So here on the right, I've got an example of, well, it just looks like galaxies. But yeah, this is a galaxy generator. So I generated a procedural system in video games for generating galaxies, and there's properties of that galaxy that we can use. We can essentially use one seed, and from that build a whole list of numbers from that particular seed, and we can use those numbers in generating something like a galaxy. So a galaxy has properties like how many stars there are, how bendy the arms are, and if you have some equation for distributing these stars based on something, there's a good paper by Ringermacher on this. You can generate galaxies from one seed, and that's really interesting. As Subpanda talked about before, we can take one seed and from that generate an entire galaxy. I just find that fascinating, So there are uses in computer science, but in video games, random numbers like this are really useful for generating stuff. So as an example, if we were to create a skyscraper, and this is where we get into PCG, so procedural content generation, what properties can define a skyscraper? So I've picked out 4 here. We've got maybe a number of floors, the width of the building itself, maybe the style and the amount of windows. If we define the valid ranges for these, so we can say that the number of floors will always be between 1 and 9, and that the width will be between 0.1 and 12. Style, we can use some kind of index into an array, and an amount of windows between 10 and 100. So if we define those valid ranges, and then using random.range or whatever, we can generate random values within those limits, and from that we can use that output for generation. But we could seed the random number generator with some value, and then generate a sequence of numbers like this, for example, like 4, 7, 2, and 65 or whatever, and using that random output, we could use one seed to generate a particular system. That's a really fascinating way of generating stuff. So just think of how you could use this, how you can use this in creative ways. A large percentage of procedural content generation systems use this this kind of approach, but it's worth thinking about how you can use it. I talk about skyscrapers and galaxies, but you can use this for all kinds of stuff. From one seed, you can generate a whole range of values based on that seed. So using one seed, you can generate entire systems based on that one number, and that's, to me, that just blows my mind. I just love that fact. The next thing I want to talk about, and we'll touch, I'm going to briefly talk about this, is coherent noise. I'm not going to go into much detail about coherent noise, mainly because that's not the purpose of this talk, and we're running out of time anyway. So coherent noise is also called procedural noise, stochastic noise, or smooth randomness. You might also hear people calling it Perlin noise. Now, it's not used quite a lot in computer science, but it is used quite a lot in games development. You'll find this in any kind of procedural content generation system. Usually some kind of coherent noise shows up. So the difference between coherent noise and uniform noise is, on the left, we've generated some texture here with just random range, just a PRNG. So you can see that it's really high frequency. Whereas on the right, we have coherent noise. In this particular instance, we have a category of coherent noise function called the Perlin noise function. And you can see that this is kind of like a cloudy texture. And the main difference here is if we drew a line across those two textures and graphed, the values. On the left, we have something here that is really high frequency. It goes from black to white, low numbers to high numbers very quickly, quite a lot. And whereas here on the right, we have essentially the same thing, but at a lower frequency. We have smooth, undulating noise, and this is what coherent noise is. It's very similar to PRNG noise, but it's smooth. It smoothly flows from one particular value to another, and that can be really useful for a bunch of different stuff. So one example is terrain generation. So if we took these two textures like this, here on the left we have something that's really high frequency, and here on the right we have something it's the same thing but essentially smoother, really. So on the left here we have something that is generated with this high frequency noise, and that just that's not a terrain, that just looks crazy. But on the right, you can start to see how we might use this for something like a ground texture or a terrain. We could think of the peaks and valleys as mountains and so forth. And this is one of the ways we can use coherent noise, is generating terrains. We can just take something that looks smoothly random, and then just throw it onto a terrain. So coherent noise functions are just smooth pseudo random noise. They usually, so unlike PRNGs, we kind of seed them and we ask for a new value. Usually coherent noise functions, we sample it with some coordinates. So we take an XYZ or an XY, and we say, what's the random value at this particular point? And then it will give us that random value. So they're different to PRNGs in one way. Small changes in the input will result in small changes in the output. Those changes will still be random, but they won't be very high frequency. And this makes it ideal for things like procedural height map generation, textures, and so forth. Even things like hair. So for things like on the right, this is just a procedural kind of hair-like texture generated entirely from coherent noise. So there's a lot of interesting stuff you can do with them. If you are interested in this, I've briefly touched on coherent noise functions here, very, very briefly. There is a whole list of coherent noise functions, and if you want to kind of go from here and learn more, there's a really good paper. In fact, it's probably my favorite paper on procedural noise functions here. So just check that out. It's a survey of procedural noise functions. Have a look at that. It describes so many different noise functions and how they work. And on that, thanks for listening. And yeah, I really enjoyed talking about this stuff. Yeah, thanks for listening. Hopefully it all made sense. And yeah, thanks.